so learning to use many of the tools as we all do. So welcome everyone. It's a pleasure to open the bootcamp and open the RL theory program at the Simons Institute. Thanks for the Simons Institute for supporting this. As Peter said, there is a huge interest in RL theory. We're very positively, pleasantly surprised about this. Thanks for everyone for the interest. So before jumping into talking about the bootcamp, I just wanted to mention that the whole program is going to run for the whole semester until December. And in addition to the bootcamp, we're going to have 3 workshops and people can register online at the website. And we're going to have dedicated Discord discussion channels as well, which are dedicated to these individual workshops. The workshops are deep reinforcement learning, online reinforcement learning, and batch and simulation in this order. And for the participants, I'd like to have a town hall meeting on the 8th of September. That's next week on Tuesday at 9 a.m. To get really the program off the ground and do brainstorming about how to structure the program for ourselves. So with that, let me go to the bootcamp introduction. This is the high-level plan for the week. So on Monday, you're gonna hear from Mengdi and me about just basics of MDPs and planning. And in the afternoon, we're gonna hear from Anka. So every day is going to be tutorials and then a bonus talk a little bit later in the afternoon. Everything's recorded. It's going to be available on YouTube. So we have to stretch across the globe, multiple time zones. It's gonna be difficult, but I hope that we can include everyone. I see that someone asked a question. Yes. How do I see what the question was? There is feedback and 2 voices, one on top of the other.
Not for me, Csaba.
Not,
it's quite clear.
Okay, all right, okay, good. All right, so that's Monday, and on Tuesday, we're gonna continue with online reinforcement learning and batch reinforcement learning. Stefan's going to give a talk in the afternoon. On Wednesday, we will hear about reinforcement learning from statistics perspective, and Ashley is going to give the talk in the afternoon. On Thursday, the control perspective, and Andrea is going to give a talk. And Friday, operations research, and Russ is going to give a talk. So that's the plan. We want to keep this as much as possible interactive. So please, at any time, if you have questions, ask here, either in the chat. I guess you can raise your hand or something like that. Also, I asked the organizers to monitor the Discord server so that if you have questions, you can ask those, ask the questions there. And then someone probably going to raise their hand here and ask me the questions. So with that, I'd like to start with the first part of the bootcamp, which is MDPs and planning. So, all right, let's get started. So the structure of, so I'm going to talk about really basic stuff for about 30 minutes, just introducing mostly definitions, just talking about definitions and some really basic results. And then Mengdi is going to come in for 30 minutes, then we're gonna take a break. And then Mengdi comes back after the break, and then I will wrap up the morning. So at the very first, let me see how I use this. At the very beginning, I'd like to talk about definitions and total reward MDPs, and then talk a little bit about the sufficiency of stationary policies, what they are, and in what way they are sufficient for MDPs, and then a little outlook at PUMDPs. So let's kick off, not even talking about MDPs, but talking just about Markov control processes. So Markov control process is like an MDP, except that we took away one piece of the MDP, which is the rewards. So what we're left with are the states, and they're collected in a set. I'm going to denote that set by capital S. So that's this set. And we have a collection of actions. Those are collected in this set A, and a collection of transitions. These are collected into this capital letter P. So what are these transitions? These are Markov transitions. So this is a collection of probability distributions, one for each state action pair. So lowercase s and lowercase a are going to denote individual states and actions. And to minimize clutter, I'm very often just going to write S and A without a comma and without parentheses and whatnot. So that means the same thing. I just don't want to introduce a lot of clutter. So what happens here is that for each state action pair, there is a distribution. So PSA is a distribution over next states. So if I need to talk about a distribution over some set, I'm going to use this notation of M1 of, and then in the argument, the set itself. So this is the collection of all distributions. So this, for every state action pair, we just have a distribution. So the idea here is that you start a process at some state S0, and then somehow you determine some action A0. So that's coming from you, the controller, the agent, or whatnot. And together, the state and the action result into a next state, that's S1. And so this S1 is distributed according to this distribution S0 and A0, okay? And then you come in and then you choose another action. And when you're choosing this action, you could use basically the first state S0 and A0 and S1, the whole history. That's what we're going to call the history. And this process continues this way. So in each and every arrow here, we're using this Markov transition kernel. So let me make this a little bit more orderly. All right, so this results in this next state, and then a new action is chosen, and so on and so forth. We can also illustrate this using a little diagram. So on the diagram, so time is discrete. So t goes from 0, and then it's incremented by increments of 1. So you start at st at time t, and you have a little controller that can have some memory, and it can also randomize. So I'm not going to denote randomization, but so this controller, we also call the maps that it implements the policy, is going to compute eventually, based on the information available to it, an action AT. And this AT is fed into this system So the system has its state and it's making transitions, these stochastic transitions. It makes a transition to the next state, which is st plus 1. And this is chosen from this PSTAT probability distribution. And so then this state comes out and is fed back to the controller, and this way a loop is closed, and this results in a sequence of state action pairs, an infinitely long sequence of state action pairs. All right. You see that there are some questions. I don't know. Why M1 is just a function of the state space? It's because okay. So the first question, why M1 is just a function of the state space? It's because these distributions are over states. I hope that now that I drew the diagram and we have this process view, it's clear that the action component is coming from a policy, and the state, the next state component is coming from the system that is being controlled. And so this is called Markov controlled process because the next state distribution only depends on the previous state and the action. So the control part is the action, and the Markovity part is that you can discard all previous states, and the next state distribution is going to stay the same. Another question, would you mind quickly go over the notation of P again? So P of S of A, so for each action pair S of A, there is a distribution over the states. So you can also think about that. You have the state space here, and then you are at some state, and then you choose some action that comes from the different state, different space, and that induces a distribution over the state space. So you end up in this cloud, like with some probability you're reaching each and every state. And then the process continues this way. I hope that this is clear. In the Markov control process, this M, we are given this S and A and P, and we're just setting up things. We're not talking about anything beyond that. All right. Okay, so given the state space and action space and these transition kernels, these are called Markov kernels as well. And if you have big spaces, then they have to have necessary measurability properties. But that's let's just disregard it for now, for the sake of time. So if you're given this, then you can fix a given state, and then you can choose a policy. And then given the Markov transition kernel, this results in a distribution over the space of all trajectories. So this is the trajectory space. So these trajectories are these infinitely long sequences of alternating state action pairs. And I hope that it's clear how this distribution is constructed. The distribution on each and every component is, like on S naught, that's a Dirac distribution put at S, and A naught is determined based on the policy, its distribution, and S1 is determined based on, like it's here, based on the transition kernel, and so on and so forth. You take all of these probabilities if you're in a discrete setting, and then you multiply everything together, and that gives you the probability of a trajectory. And if you are in bigger spaces, then you can do this, extend this idea to these bigger spaces in an appropriate manner. And so here the important thing is that I'm going to use this notation of P of S and pi, which is a distribution over these infinitely long sequences of state action pairs, these trajectories. So there's a distribution over trajectories. And if you have a probability distribution, then of course you can introduce an expectation operator, and I'm going to use a similar notation for that. So this is going to be the underlying expectation operator. And if we have an initial state distribution, mu, so here mu is a distribution over states, then a similar construct leads to distributions over trajectories, and similarly, we can introduce this expectation operator, E of mu of pi. All right. I think I did answer pretty much all the questions, I would say. I don't understand. Someone said yes, Csaba. All right. Okay. So we have constructed this probability distribution, given an initial distribution, an initial state, a policy, and a Markov kernel over the space of trajectories. So what are we going to do about it? So we need a control objective. For the control objective, we're going to use rewards. So we pick a reward function R. So this is your reward function R. Sorry. Okay, so it maps state action pairs to real numbers. So this is my notation for real numbers. And so if you have a trajectory, I'm also going to denote trajectories by just age. So if you have this trajectory, then you can assign a return to the trajectory, which is just the sum of rewards along the trajectory with an optional discounting. So these are called, this is also called the immediate reward function, because you receive these when you're making a transition. And here this gamma is this discount factor. And many times we choose it smaller than 1. And if the rewards are bounded, then this would ensure that this function over the trajectories is well defined. So capital R is the return function, and this sum is just called the return. Okay, so once we have the return, we can define the value of a policy. So the value of a policy is if you start a policy at a particular state of S, is denoted by V of pi of S, and it is defined as the expected value of the return. Okay, so recall that so this P is the probability measure over the trajectories, and so this is basically if you have, you know, uncountable many trajectories, then you would need to use an integral notation. So let's go that way. But if you have finitely many state action pairs, then you can just enumerate all the trajectories. There is going to be countable many of them, and then this integral becomes just this sum. All right. There is some beep that is annoying, but I don't know about that. Sorry about that. If I knew what is the source of that beep, I would get rid of it for sure. Anyways, so this is the value function. So I'm sorry. So this is the value of the policy pi in state S. And if you collect all these values, then V of pi can be viewed as a function that maps a state to a real value. So this is going to be called the value function of a policy pi. And there are many variations. So the variations would include, you know, there is no discounting, there is discounting. Okay, maybe the horizon is going to be finite. So maybe age is finite, or maybe age is infinite, and so on and so forth. Sometimes you restrict the set of actions that are available at the given state, and you have this admissible set of actions. And sometimes you consider other criteria like the average cost. I'm not going to talk about this. It would take too much time to talk about these as well. All right. So the control objective, it is shown here in the bottom. So let's focus on this. So the control objective is to find a policy pi such that for every single state, this policy maximizes the values that can be achieved if you're free to choose a policy, even depending on pi. So this value here, this is defined as the optimal value function, or the optimal value at state S, to be precise. And if you collect, again, all these values together, then you get V star. And V star is just this map that maps states to reals. And this is called the optimal value function. And solving an MDP means that you are able to find a policy pi such that this policy achieves the best possible value at every single state. So in planning, we're asking the question of like, how can we do this? So planning asks the question, given an MDP, what is a computational procedure that gives us an optimal policy? So how do we get a procedure? And so when we say that we are given an MDP, I'm not too clear about what I mean about that. So in the next part, Mengdi is going to talk about the case when we have a finite MDP. So in this case, the number of states, the number of actions is finite, and you can enumerate, you know, like the state transition matrices. They just become a big table, and you can enumerate everything. The value functions become vectors, and you can, in this case, talk about that you can find or not an optimal policy, and how long does it take to find such an optimal policy. given the information that is fed to you. So the information could come in this form that you're giving these big tables, and it's a good thought exercise just to think about how we would do this computation. But of course, that's not really practical. Many times we have much bigger number of states and also large action spaces, so that this enumeration is not practical. In the last part, I'm going to talk about what we're going to do in those cases. Before that, I just briefly wanted to mention one thing about effective horizons and discounting. So if you have a discount factor and you're shooting for an epsilon accurate evaluation of a policy, then what you can do is that you can cut this infinite sum that was, so in this case, the horizon was infinite. So you can cut this infinite sum. Sorry. At some finite horizon, this h gamma. And you can set the h gamma to be like log 1 over epsilon 1 minus gamma divided by 1 minus gamma. And so if the reward function, I'm going to assume this, takes values in the 0, 1 interval, then this ensures that you don't lose much by cutting the trajectory short. And so here, this h gamma, and sometimes it just like 1 over 1 minus the gamma ignoring the log is called the effective horizon. So this is just based on, you know, like taking the maximum values here, which are 1, and like the maximum differences that you can get, and summing the infinite series from h gamma plus 1, sorry, from and so this is just going to be gamma to the power of h gamma plus 1 times 1 over 1 minus gamma. And so if this is smaller than or equal to epsilon, which is ensured by this choice, a little calculation shows that, then you can be sure that you're not missing much in terms of the rewards. And so if you're interested in epsilon accurate evaluation of your policies, then the lesson is that you don't actually have to consider infinitely long horizons, but you can cut the horizons short, and this is used a lot in a lot of different arguments. That's why I put this up first. So now the next topic is, okay, so we set out to find an optimal policy, or maybe just an epsilon optima. So I didn't say much about that, but the epsilon optimality would be to find some policy pi such that v of pi is bigger than or equal to v star minus epsilon. And let me write just one. So this is a vector notation. It means that for every state, the value of the policy would be above the optimal value minus epsilon. So that would be the epsilon optimality criterion. And so the question is, in what form should we search for policies like this? And in a nutshell, the answer is that we should, it is sufficient to just look at stationary policies. So what are these stationary policies? So a policy could have memory, could use past information, previous states and previous actions when it comes up with a distribution over the next states, if it uses randomization, or it could be deterministic. So it may or may not use memory and may or may not use randomization. So let's first stick with randomizing policies. If the policy uses memory, but only step counter, so it remembers like how many steps we are in the process, and depending on that, it chooses a distribution that is based on this counter and the last state, and the distribution is over the actions. So then we're talking about Markov policies. And a policy, which is a Markov policy, which doesn't use the counter, so it doesn't have any memory. So it could also be called memoryless policy. Maybe that's a better name, memoryless, or pure state feedback. So these are all different names that people use in different parts of the literature. Then you arrive at stationary policies. So the claim here is that from the perspective of finding an optimal policy, it is going to be sufficient to just focus on stationary policies. Why is that? So the reason that holds is because of this little proposition. So this proposition says that if you take any distribution over the states, and you take any policy, an arbitrary policy that can use memory and randomization and whatnot, then you can always find a stationary policy such that the value of the stationary policy when the policy started from this initial distribution is the same as the value of this arbitrary other policy when it started from that distribution. So here, the value is defined. My pen is misbehaving a little bit. So the value of a policy pi is defined as usual the expected value of the return, and of course you can exchange. So let's assume for simplicity that rewards are bounded. That's always very helpful. Then you can exchange the infinite sum and the expectation. By the dominated convergence theorem, and for simplicity, let's assume that you have countable many states and actions. Then you can replace this expectation by this sum, where you take the probability that the state at time st is s, and the action at time t is a, and just multiply this with the individual rewards and take the sum over all possible state action pairs. And so we can call this, just do one more step. So then we can swap the sum over the state action pairs and the infinite sum. And we can just collect the terms, and we see that this expression arises, which I'm going to denote by mu of pi at SA. So this is the definition of nu of mu of pi of SA. And this is called the discounted occupancy measure. Let me just put this here. So for each state action pair, we're assigning this number, which is the sum, discounted sum of the probabilities of the process visiting that given state action pair at a given time step. And so this is called a discounted occupancy measure. Okay, so towards this proposition, so let's recap. So we want to show that for any arbitrary policy, it suffices to consider just a stationary policy to reproduce the policy's value from a given initial state distribution. So for this, we started to rewrite the value of this policy pi, and we find that this value can be written basically as the inner product between the discounted occupancy measure, or just the occupancy measure, and the immediate reward function. So you could just write this in a short form like this. If you introduce an inner product notation, you can view this just as a big vector, and this is a big vector, and so this is just inner product between these two guys. And so based on this, it's quite clear that a proposition would hold true. We would see that it holds true if it holds that if I choose an arbitrary policy pi and I take its discounted occupancy measure, then I can reproduce this discounted occupancy measure with the help, I can produce the same occupancy measure as this with the help of a stationary policy. So the proposition will be shown to be true if it holds that for any, oh, I had a lot of space here. So for any policy pi, so it's enough to show that for all pi, there exists a pi prime. For all mu and pi, there exists a pi prime, such that the nu of mu of pi is equal to the nu of pi prime. So how are we going to do this? It's a simple procedure. We are going to explicitly construct this pi prime. And the idea is just to marginalize. So take this, so fix this arbitrary mu and fix the arbitrary pi. So this gives us this occupancy measure mu of pi, which gives you, you know, this number for every state action pair. And we need to produce a stationary policy. A stationary policy is a distribution over actions given a state. So a simple way of doing this is to marginalize, and a good way. So this is how it's going to work. So just we just take this discounted occupancy measure, and we divide by the marginal. So mu of pi of s is going to be the sum over all the actions of the same thing, and if this is non-zero, and we assign an arbitrary distribution if this happens to be 0. So this is pi naught is just an arbitrary distribution over actions. It doesn't matter what distribution we choose. So I don't know whether I should go through why this is enough. Maybe I go through why this is enough just very quickly. So let's define this Markov kernel pi of s of pi prime of s prime as you know, this given a state S, policy pi prime first chooses an action A with some probability, and then we are making a random transition according to the transition dynamics that we have. And so note that this can be written as the sum of because of the definition of pi prime. So just plugging in the definition of pi prime. Yeah, just this form. Okay. And now the argument goes as follows. So if you take this marginal distribution, then this is just the, by definition, this discounted sum of visitation probabilities of this particular state. And you can break the sum into two parts, and you will see this argument many times. So this probability distribution, of course, for t equals 0, it's mu of s, because that's your initial state distribution. And for all the others, you can just pull out a gamma, and you get gamma of t plus 1 of p of mu of pi, and s t of pi of s. And so now we're going to use the Markov property. So just sum over s prime and a, so law of total probability. Sorry, this is just the, because I pulled out the gamma already. So I want to bring in the occupancy measure. That's why I'm doing this. So I write this probability, I expand it based on what the previous state action pair could have been before we arrived here. And then that introduces the Markov kernel. So we're going from S prime using action A to state S. And now you can see that this is just mu of pi at S prime and A. And now you can start to see that we have the same expression as I don't know whether it's clear, but I'm pointing. We have the same expression as here, except that S is here, S prime, and that S prime is S, so for, swap S and S prime. So using this, we get that this is mu S plus gamma times sum of S prime and A of pi prime. Sorry. I need to bring in mu of mu of pi s prime, because I need to divide and multiply. And then I have the sum of reactions. I can replace that just with this pi prime, a s prime, a s prime, a. And now this is nothing but the transition kernel that we introduced before. This is p of pi prime, s prime s. And with a vector notation, what we derived is that mu of pi is equal to mu plus gamma times mu of pi p of pi prime. And now the argument is that this equation has a unique solution in terms of mu of pi. And by repeating this same argument, you can find that the unique solution of this equation is actually mu of pi prime. So it follows that mu of pi is equal to mu of pi prime. So uniqueness gives you this. And apply this with this whole same reasoning, this pi set to pi prime. Right. So that shows that this construction does everything that we wanted. So the corollary to this, I'm using a little bit too much time. So corollary to this is that there exists a pi, which is a stationary policy, which is optimal. So why is that? It's because we showed that stationary policies are sufficient to reproduce the values for any given initial state of any policy. And so first you can construct a policy. So for really the existence, not absolute optimality, you need to have some additional nice structure assumptions. But for example, if the state action space is finite, okay, so let's be specific. State action space is finite. Then you can first find a policy which is optimal, right? So the optimality definition was that the policy needs to achieve the maximum value at every state action pair. If you start with an initial state S, so that's a U that is a Dirac at S, then you just have to maximize this inner product. And so you can find a policy that really achieves that value, and that's because the space of occupancy measures, it also follows from this derivation, is a nice compact convex set. This you can see from somewhere here in the middle, like you start here and the occupancy measure satisfies this equation here. So you can plug this in and cross out this mass. And so that's just a linear constraint on the occupancy measure. And you can show that if you have some other constraints, non-negativity and some normalization constraints, then every element, every measure, every function of state action pairs that satisfies these linear constraints occupancy measure, and it's a nice convex compact set. And then you can find a policy that maximizes the value for a given state. And since the policies are not restricted, you can also stitch together policies and find a single policy that looks at the initial state and say that, oh, like if the initial state is this, then you just use this policy, which is optimal for that initial state. You stitch the policies together because policies can remember what was the very first state. And so this way you arrive at a policy, which uses memory and remembers the very first state and is optimal. And once you have that, you can reproduce the value of this policy by a stationary policy. And which stationary policy? Well, this stationary policy doesn't depend on what the initial state distribution is going to be. It happens to be true. So it follows that there exists a stationary policy which is optimal. I guess maybe Mengdi is going to talk a little bit more from a different angle about this. And it also follows that there exists a policy which is deterministic, which is optimal. All right, my time's really up. So I just wanted to say a few words about partially observable MDPs. The previous figure showed that the controller or policy receives the state, and very often it is the case that the state, which is a summary of all the past information, is not available for measurement. And a more general way of thinking about control systems is not to assume that the state can be observed. So still maybe there is a state that is being updated, but instead of having a Markov kernel that gives you next state and then you observe the state, you have a Markov kernel here, Q, which gives you a pair of states and actions and states and observations. So this is next state, obviously, and this is an observation that is going to be fed to the controller. So in this case, the controller can only use the observation, and in a way, this is the real deal. This is how most of the time control systems need to interact with their environments. And the question is, can you extend any of the things that we were previously said to this case? This happens to be in a way true. So if you start with an initial state distribution nu naught, which is known, given to you, then the marginal distribution of the state given a history at some time step t, let's denote it by mu of t, satisfies a recursive update. So mu of t can be seen to be computable as a function of the previous distribution, the last action and the last observation, and for this you just need to use Bayes rule basically. And it happens that you can also think about mu of t as being randomly sampled from some underlying transition kernel. So this way, we're lifting the problem of computing optimal policies from policies that depend on states to policies that depend on distributions. So an optimal policy in PAM-DPs would, keep track of this random measure, this belief state or belief distribution over the state space, and would use that as a summary, and then you can try to generalize results, the constructions, and so on and so forth. All right. So I think that with that, I'm done. Let me see whether, well, I used a lot of time, so should just wrap up. Oh, what happens when the reward is not bounded? Well, you need all kind of regularity conditions, or you could have costs even, in order to be able to define values, and some policies may not have values. The same problems happen when you don't use discounting, And in this cases, people assume more kind of regularity conditions so that to make sure that even the notion of optimal policies is well defined. All right, Mengdi, are you around?
Hello. Yes.
Okay. Sorry. So we ran a little bit over time. Sorry about that.
That's all right. I'll try to be very high level.
Okay.
Let me see.
Great.
If,
So the stage is yours.
yeah,
I don't actually want to not share screen.
Yeah, I can share my screen if you're sharing yours.
Yeah. Okay. Okay. Actually, how do I unshare? I'll share. Okay. Stop. Okay. I think it's good.
Okay. Does it work?
I think so. Yes.
Okay. So next, we want to talk about the very basic methods and complexity results for planning in Markov decision processes. And like as Csaba has mentioned, like reinforcement learning is a very broad problem, and there are many problems that are extremely hard, like partial observable Markov decision process, and also for continuous problems with unbounded space. Usually the problems become harder, and there's a lot of like nuances. So to talk about complexities, again, so we want to focus on the simplest finite state, finite action Markov decision process, and assuming everything is bounded. So this is a notation we are going to use. We have a finite set of states, a finite set of actions. At each state and action, we have a reward, which is a scalar. And we have a collection of state, action to state transition probabilities. So all of those are input to the algorithm. And based on those, we're trying to solve the optimization problem and find the optimal policy that maximizes the cumulative discounted sum of rewards. Okay, so this is just a statement of the problem. We have already simplified it to the most. So no unboundedness, no partial observability, everything finite. Okay, so usually we call this tabular Markov decision process because we don't really have much structural information or additional prior knowledge here, just a discrete computational problem. Okay, so what are the basic methods? So first, whenever we talk about solving Markov decision problems, we usually always write down the optimality condition, which is known as the Bellman equation or the optimal Bellman equation. So the optimal value function, which we call the V star.
Mengdi, your slide is stuck at the title slide.
Sorry, I think that happened to me a lot. I have to stop the presentation mode. Does it work now? Hello?
Yes, I see the, a Bellman equation, yes.
Okay, yeah. So I was talking about the basic notations and now the Bellman equation. Okay, so we want to compute the optimal value function. And in the discrete case, the optimal value function is just a vector. And the dimension of the vector V star is S, the number of states. Okay, so there are three major classes of deterministic algorithms, but they turn out to be the foundation to many learning algorithms. So we'll just go over them one by one, but very briefly. So the first one, actually, before we go over them, we need to introduce a notation called the Bellman operator. So the Bellman operator comes from the Bellman equation here. So the Bellman operator is going to be the operator that maps some value function here to the left-hand side. So it's defined in this way. So we can apply the Bellman operator T to any value function. And it will work in a way as if it is doing one-step look ahead. Basically, by treating this V as the value function at the next step, and try to compute what's a better value function at the current stage. Okay. And know that this is definitely a nonlinear operator. And we also need notation for the Bellman operator. We call it T-pi for a fixed policy. So if we fix the policy, then this Bellman operator is really just a linear operator. We simply try to evaluate the expectation of future value by using the probability for choosing actions based on the policy, and also by using this V function as the next step value function. Okay, so the Bellman operator has a few very elegant and fundamental properties that are basically the key to a lot of analysis. So the first property is the contraction property. Wait a minute, my apology. I think I missed the discount factor gamma here and here. We need to have discount factors. Okay, so once we are talking about discounted Markov decision process with gamma between 0 and 1, so it's pretty easy to prove that the Bellman operator is strictly contractive with respect to the L infinity norm, and the modulus of contraction is bounded by gamma, the discount factor. Okay, so we don't have time to prove it now, but it's really an easy exercise. Another important property is that the Bellman operator is monotone, meaning that if we start with two different functions, V1 and V2, and say V1 is pointwisely greater than or equal to V2, and after we apply the Bellman operator T to both V1 and V2, this relation still holds. So monotonicity in value function is going to be preserved after applying Bellman operator. Okay, so based on the two properties, we can see that the Bellman operators are very nicely behaved. And also it's easy to show that the optimal value function V star is the unique fixed point of the Bellman operator. And the value function for fixed policy is the unique fixed point for the Bellman operator T pi. Okay, so those are very basic properties, but we do note that for especially this contraction property heavily relies on the fact that we have a discount factor. So in some way, like the process always returns to some dummy state with probability 1 minus gamma. So we can think about by using a reduction. So somehow the process always returns to a fixed point. But that's why we have contraction. But if we don't have the discount factor, if we talk about undiscounted infinite horizon MDP, then the property becomes tricky. And one can show that this property no longer holds for L infinity norm, but holds for a variant of L1 norm. And there's another story, a longer story there, which I won't be able to tell today. Okay. So the first very basic algorithm is called value iteration. So the algorithm is extremely simple. It basically says that we start with any V0, any vector of dimension S. And then we just apply the Bellman operator T to that vector over and over. So this is called value iteration, but this is really just another way of phrasing dynamic programming. We're just doing backward induction. Okay. And it's about the value iteration, a very basic result is the value iteration converges exponentially in L infinity norm. And this is a simple corollary from the contraction property of the Bellman operator. So basically, as long as we are iterating the Bellman operator, our value functions are going to converge very fast to the optimal value. And similarly, we can always derive the policy from the value function, and the policy will converge to the optimal policy. Okay. So if we try to do some finer calculation to calculate all the arithmetic operations needed in applying each value iteration, so we can show that the runtime complexity for value iteration is the following. So it's of the order S squared to A. So S squared times A is really the size of the transition matrix. So it's really the size of the input. So this time complexity is linear to the input size. And also, if our discount factor is very close to 1, then the convergence rate will be slowed down. Okay. So a slightly more complicated algorithm is known as the policy iteration. So instead of iterating Bellman operator in the value space, we try to do that in the policy space. Okay. So again, we start with an arbitrary policy pi0, but we try to improve it incrementally. So to improve a policy, we always try to evaluate it first, meaning that we want to first compute the value function corresponding to that policy, which is equivalent to solving a linear system of equations. But we write it abstractly like this: t pi k times I would say t pi v pi equals v pi. We are trying to solve this equation. Okay. So once we solve this equation, we obtain the value of the policy pi k. We try to improve it by again doing one-step value iteration or one-step look ahead. So we're trying to find this new policy pi k plus 1 such that by applying this policy for one step, we're actually doing the optimal Bellman operator. It's actually equivalent to applying the optimal Bellman operator. Okay, and in a way that's similar to the proof of value iteration, but slightly more complicated. One can show that policy iteration also converges linearly, and the modulus of contraction is again determined by the discount factor. And for undiscounted problem, there's again a longer story which we don't tell today. So why do we care about policy iteration? It looks like it's more complicated than value iteration, right? So what happens is the algorithm is iterating over the space of policies. The space of policies is in some way a smaller space than the space of value functions. And there's some subtle difference. For example, it's known that policy iteration is strongly polynomial, but value iteration is actually not. But however, if we just try to implement policy iteration in a straightforward way with just a regular equation solver, we call that whenever we try to do policy evaluation, we need a linear system solver. So if we just use a naive solver, the complexity won't be too good. So we actually get quadratic complexity with respect to the input size. Okay, so that's the second approach. And the third approach is quite different from the first two. So again, recall that we are trying to solve the Bellman equation. But now instead of trying to utilize properties of this T operator, we may equivalently rewrite the Bellman equation into a linear program. Basically, we're trying to say that, hey, we're trying to find this value function such that left-hand side of the Bellman equation is always greater than or equal to the right-hand side. And then we try to lower the left-hand side. So that's the intuition. And this requires a little bit of proof, which is, again, a very nice exercise. Okay. So if we can write the Bellman equation into a linear program, it's going to be a linear program of dimension s times a times s. So it's going to be a big linear program. So what's interesting is we can look at the dual of this linear program. So this is like the linear program in the space of value functions, right? But if we try to write down its dual, we're going to associate the constraint with Lagrangian multipliers. And the dual program has a very interesting interpretation. So the dual variables, we call it lambda. Okay, so it turns out that the optimal dual variable in the linear program corresponds to the discounted occupancy measure under the optimal policy. So in some way, lambda star tells us about some long-term stationary state action distribution when a good policy is chosen. And if we try to interpret the dual LP, we can see that, let's look at the constraint first. This is a linear constraint, and this constraint is equivalent to requiring that this lambda is the occupancy measure corresponding to some policy. Okay, so now we are searching in the space of occupancy measures that are possible under this MDP. And within all such occupancy measures, we try to find the one such that we maximize its inner product with the reward. So the inner product between an occupancy measure and a reward is exactly the value function. So basically, this says that we are searching, we are optimizing over the space of attainable occupancy measures directly. And that's the dual problem. Okay, so if we think about this problem purely as a linear program, and we try to use the best interior point method or the best LP solvers. So there are a list of best known results for using LP solvers to solve, for using interior point methods to solve this problem. And again, we can see that even this better result has superlinear dependence on the input dimension. Okay, and comparing to the one we had here, this value iteration, this simpler algorithm actually has linear dependence. So it might seem like LP methods might not be the perfect algorithms for solving this particular problem. So we can actually see why this is true, because if we are treating this problem as an LP, we are not utilizing the contraction and the monotone properties of the Bellman operator. We are only using the fact that it's a plain LP. Okay. But one thing interesting is if we look at this particular dual linear programming, okay, we realize that we have a space of state action occupancy measures, right? And if we are familiar with LP, then this space of lambda is a big polyhedron. And we have many vertices on this polyhedron. And it turns out that the vertices of this LP constraint corresponds to deterministic policies. Okay, and one can further show that the policy tuition, the algorithm that improves policies one by one, so that algorithm is equivalent to a variant of block simplex method applies to the dual problem. So there are many interesting correspondences there that are fun to analyze. Okay, so last slide. So the best known upper bound to my best knowledge is this one. So this is a runtime complexity obtained by using a variant of value iteration, but with a lot of algorithmic hacks and randomization to help accelerating it. And as we can see, this complexity is almost linear in the input size. So we have some multiplicative factors by this logarithm, and there are some additional factors, but hopefully this is much smaller than input size. So we will say this is almost a linear time solver, and it could be the best we could expect. And as for lower bound results, so there was this seminal paper by Papadimitriou and John Tsitsiklis. So they show that solving MDP is definitely a polynomial time problem, and it's p-complete. But although MDP is simple and nice, but if we have partial observability, the problem becomes really hard. So solving POMDP is p-space hard. It's even harder than NP-complete. So it's just much, much harder if we have partial observability. So having states that give us the Markovian property is really a blessing. Okay, and also there was this classical result that if we try to computationally solve a continuous state, continuous action MDP with smoothness, then the runtime is going to be like this. So basically, is going to be exponentially bad in terms of dimension of the state vector n and action vector m. Okay, so finally, I just want to say that most of the results for discounted MDP extend pretty easily to finite horizon MDP. So as Csaba mentioned, so it's pretty straightforward to have to construct a reduction. For example, we can always approximate a discounted MDP with a finite horizon one by just choosing the horizon to be long enough to be like this order. And the other way is we can always approximate a finite horizon MDP by picking a good discount factor in a discounted MDP. So those results for discounted MDP almost all hold for finite horizon MDP. But if we talk about undiscounted infinite horizon, then the problem becomes much harder, and it's not within the scope today. Okay, so I'm going to stop here, and we're going to have a short break, and then we'll continue in probably 20, 30 minutes.
Right. So there is this Gather Town link. It was posted in the chat somewhere. I think we should just head there, and then we can continue having some conversation there. Okay, I'll be there. See you soon. And then we come back at in 20 minutes. Okay, so there is the link again. If you haven't used Gather Town, you just click on this, and then your little avatar, and then you can go near people, and then if you're near to someone, then you can talk to them. All right, I leave this open, and just yeah. Can we also copy the this link to Discord, maybe?
Yeah, I put it in a couple places on Discord.
Okay, good,
Yeah.
awesome, thank you.